And this lecture is planned to be our last lecture here. So I plan to talk about the GAN, Generative Adversarial Network, which is quite popular in recent years. Yeah. So before that, I first show you something. So could you see this person, this picture? Is it visible for you, Xinyu?
Yes, it's visible for me.
Okay, good. So this is a picture, right? It's a picture of a human being, a face. Actually, this person doesn't exist. So that's why you see this website is called thispersondoesnot exist.com. These pictures are all generated by a generative model. That's again generative adversarial network. So you can refresh this website and all these pictures, yeah, this one or that one, are all fake face, but they really looks so amazing, so realistic, right? Really looks like something real, a human being. This is fake picture. This is all generated by the GAN model. And GAN is actually quite famous in being capable of generating very high, very good quality pictures or data samples compared to other generative models. So in this lecture, we will see how GAN is working and why GAN can be good at generating very good quality data samples. Okay, so actually I didn't prepare slides for this lecture, and before I also do not use the slides for GAN talking. I just use the Blackboard. So I hope here we can also just use the screen to write all the underlying mechanism to help you understanding it. Okay, so GAN is a short-term name for Generative Adversarial. Sorry, adversarial. How to spell? And maybe this is right. Network. This is invented by Young Get Fellow. This is the author of this method, and he is now currently working in OpenAI. And the motivation to introduce this kind of adversarial training or learning is trying to beat the previous generative model. And we know, in general, the generative model is based on the maximum likelihood estimation, right? By the way, let's repeat the task again here for any kind of generative adversarial network. And the goal is what? The goal is, so given some data, the general task here is given some observation, right? So we have a lot of observations. Suppose we have n observed or a collection of the training data, and we assume these observations, they are kind of generated by some data distribution function. So you can call it p data or p real, and we will use a short letter r to represent the underlying distribution function for our collection of the observation, right? R here means real or data. And the task for a general generative model is trying to construct a model. This model can be a parameterized function, like you have some model parameters theta. So you want to tune the model parameters theta here to let the generative model approach the underlying data distribution function, PR, right? So you want to find which kind of theta parameters can let your model to be very similar to the data distribution function. That's the general task here. Okay, so we know that the very general principle is what? We repeated already thousands of times. The general principle here is maximum likelihood estimation, right? MLE. So basically, this is trying to let all the observation functions, all the observation we have, the X, the big X here, to have a very large chance to be appeared under our model, right? So the likelihood is just the probability of each observation. So each of these xi that's really existed already, right? That's our observation. So we want to maximize this likelihood. And usually all different generative models are based on this principle, using this maximum likelihood estimation. Maybe a taxonomy can be helpful here. For classifying different algorithms for generative models, if the algorithms are really using this MLE estimation, this maximum likelihood estimation, you can classify algorithm depending on how you parameterize or how you construct your generative model, this p-fit of X, depending on if you have an explicit or implicit p-fit of X. If our generative model, this p-fit of X, is explicit, that means we have a tractable way to express this model, right? For example, a very simple case is for one-dimensional case. Suppose you have a lot of training data points, example, yeah, that's a lot of training data points, 1D, X, and here you want to model the P of X. So you can use what? Maybe you can use a Gaussian distribution function, try to model this data point you have, right? And then you use the maximum likelihood estimation. You just put all your observations into this Gaussian distribution function. The parameters, you can choose it to be the mean and the variance, right? So tune these two parameters to let your likelihood to be maximized for these observation functions, for this observation data point, okay? Or if it's not one-dimensional, but maybe two-dimensional or three-dimensional, so you can also construct a multivariate Gaussian distribution function. If your data set looks like x1, x2, for example, for two-dimensional keys, you have data points looks like here, you can visualize, then you can use what? You can use a two-mode Gaussian distribution function to model this, right? So you have two sets of mu1 and the sigma, two sets of the mean vector and the sigma matrix. Basically, once you have some expression, you have some formula for this p-fit of X, you can easily maximize this likelihood by gradient ascent, right? You just increase your likelihood every time that you can do. In some other cases, like the model, like the data might looks very complicated. So using such very simple Gaussian distribution is not a very good choice. Then you can use, like, for example, the fully, that's called fully visible belief network, fully visible belief network. This is basically trying to decompose the p-theta of X into a product of a chain, using the chain rule to decompose this p-theta of X to be some conditional distribution. Let me write it. Okay. Xi, x1, x2, xi minus 1 I equals 1, 2, depending on your data points dimensionality. Suppose our data points are all located in a key dimensional space. Yeah. So you decompose the p fit of x into a series of products of conditional probability, right? And for each conditional probability, you can use, for example, a neural network to represent. And the advantage of this kind of decomposition is once you have some data point x, you can evaluate the probability under your model. So you just throw your x into this formula, you can get what's the probability that this x can appear under my model, right? So once you have this evaluation ability for any given x, then you can insert this into your likelihood formula. You just increase it. Actually, this kind of way is very similar to the variation approach in physics. And recently, we also have a paper that's applying this kind of strategy, but it's using a autoregressive network. So people also call it pixel CNN. Once the data points are picture-like stuff, and we applied this strategy to generating the XY model configurations, and it can really achieve very good result. So this is the explicit classes. And in some other cases, still you want to have some explicit estimation for this p-fit of x, but because this estimation for the p-fit of x is not tractable, so you can use some approximations. Like in last lecture, we used VAE, right? This variational autoencoder that's basically trying to approximate this p-theta of x using a variational lower bound or the evidence lower bound using this elbow. Right? And this elbow can be viewed as a variational free energy, as the case in physics. Right? So basically, once you want to have an explicit evaluation for this p-fit of x, one way is you construct a formula for your model, or you use some lower bound for this p-fit of x. That's all going into this explicit classes. Then the second class is we do not have this explicit estimation for p-fit of x. We only implicitly know that we can approach some p-fit of x, and we can tune the model parameters to let this implicit, this underlying model distribution function to approach the true data, the real data distribution function. And in this lecture, what we were talking about, the GAN, can be classified into this category. There, we do not have the explicit estimation for the model probabilities, like for given x, like this can be a picture or some sequence data, whatever. We do not know how to estimate p-theta of x, but we have the ability to let this p-theta of x to be very close to the real data distribution function, the probability values. We have this ability. So now let's look into why we introduce such an adversarial learning. As I said, all the general principle for the generative model is using this maximum likelihood estimation. So first, I want to show you that this maximum likelihood estimation is actually equivalent to minimizing the key error divergence between your data distribution function and the model distribution function once you are using this MLE principle. This is actually quite easy, that we know that MLE is what is trying to find an optimal parameter values theta star. And this optimal value is the one that can maximize the likelihood, right? And the likelihood is defined to be the product of each observation appeared under our model, right? And as we said, because the probability value is usually between 0 and 1, so you time this so many times, it will give you some numerical underflow problem. So we invert it to be the log. And this logarithm operation will not change the result of this argmax operation, right? Log this sequence of products is just summation of log, right? This is already very familiar to you, and you can insert 1 over n constant here. This is just what? This is just the expectation of log p theta of x under the real PR, under the real distribution function, right? And actually, this is an empirical data distribution function because we only use this example, this p of xi, to estimate this average. Only when n goes to infinite, this can be exactly equal to each other. So you can then remove this tilde, set this to be the real data distribution function, but not the empirical distribution function. If you write it using the integral format, this is what? This is the integration of p real x log p model, right? The p theta of x dx, right? That's the same. This two is the same, just to write it in different format, right? And is this familiar to you? This is just the cross entropy. Right? Here, we can actually add one more constant term. Let's write PRX log PRX dx. This is what? This is the data entropy, right? Data distribution entropy. Because in this term, there's no theta being appeared, right? So this will not influence the argmax procedure. You can combine this into the whole term. Then you will know this is, you can write it in this format, dkl, prx, and p theta x, right? These two terms is just what? Is just PR log PR over p theta. You combine these two terms, you get this key error divergence. If you still remember, in last lecture, we defined this key error divergence. This is kind of a metric to measure the dissimilarity between these two distribution functions, right? And some properties for this key error divergence is that first, it's positive. It's always larger or equal to 0. And when this key error divergence can be 0, the equality happens if and only if p real equals p theta everywhere or almost everywhere. If it's a discrete distribution function, then this should hold for every data position. If it's a continuous distribution function, then this should hold for everywhere. Okay, so now from this very simple derivation, we see that maximum likelihood estimation is equivalent to minimizing the key error divergence between the real data distribution function and our model distribution function, right? Actually, this key error divergence perspective is the most underlying drive force for all different kinds of generative models. This is the essential mathematics that because this provides us a measure, kind of a distance, even though this is not exactly a distance, but this kind of a measure, how close the two distributions are with each other, right? Okay, so last lecture, the VAE, variational autoencoder we talked about, is also using this key error divergence as the driving force to optimize. And you also say, if you run the code, you will see that usually the generated pictures or images are not very clearly looks like, even though it looks like it's from the real data distribution function, but the quality is not very sharp, it's not very crisp, right? This is a very general problem for all kinds of generative model. Once it's using the maximum likelihood estimation or using this key error divergence, it's because of the non-symmetric property that key error divergence between PR and P theta doesn't equal to key error divergence between P theta and PR. It's not symmetric. This is kind of the reason why the generated data samples are a little bit blurry, not very crisp. Now let's see why this is kind of a drawback. First, let's see the key error divergence between data distribution function and the model distribution function. What's the definition for this key error divergence? It's integration P real log P real over P model, right? You have the dx. So always remember that the P real and P model, they share the same argument, that's x, P real, P theta. And the other way to measure this distance is P theta and PR. PR divergence is the integration of P theta log P theta over PR, right? These two are different from each other. They are not the same. That's why key error divergence is not exactly a distance measure. It's only providing you some feeling about the similarity. And also, these two measure formats, they share or they are sensitive to different aspects. If you use that to be your objective, to be your training guidance. So let's first see the first one. We know that once you use some metric to be a loss function, you always try to reduce it, right? You try to let it to be as small as possible. Now, suppose you have the data here. The real data distribution looks like something, let's say, let's just randomly generate a not so simple, but also not so complicated distribution function for the real data. So we use this solid line, the solid curve to represent this is the PR X. Imagine in this formula, if P theta of X is very small and the PR is finite, what will happen? If P theta is very small or approaching 0, then this is what? This is very large, right? So this very large means what? Means the training will always trying to avoid this case, or it will punish this situation. Which situation? When P theta is very small and PR is finite. That means what? That means in these two regions, PR is finite, right? Around these two peaks. Around these two peaks, the algorithm, the training algorithm that use this key error divergence to be the objective will punish the model to be very low. So there's no situation using this training that your model locates here. The model will always put something in these two peaks, right? Once you are using this KR divergence, because once your model probability is very small here, then this log will be giving you a very large number. So that means your loss is very high. The training will punish this very strongly. But in this region, the region that you have low probability density for the real data, even though your P theta or your P model is high, that's fine. Why? So PR equals 0, P theta is finite, log 0 is very small. So that can be acceptable for the training algorithm here. So once you are using this KR divergence, very probably your output or your training result for the model will look like this dashed curve. So I will use dashed curve to represent that's the P theta of X. This is what? This is something called, you can call it mode mixing or mode averaging. And especially in this range, your generated data is actually very off, very far away from the true data distribution function. And that's also why once you're using this KR divergence to be your guidance, your generated pictures or images are kind of blurry because you always average different modes together, right? And if you remember, when we do the VAE training, the variational autoencoder training, we are using this KR divergence, right? Okay, now if you want to change your objective to be this KR divergence, yeah, P theta with P real data. Again, the goal is trying to reduce this KR divergence, right? Try to reduce this loss values. And for the same data distribution function, what will happen? So let's try to find which case is very severe that the model will, the training will punish strongly. So when PR is very small, yeah, and when P theta is finite, this will be strongly avoided or strongly punished, right? That means here in this point, PR is 0. The real data distribution is 0, right? So in this point, P theta cannot be finite. So this case will be avoided. But in these two regions, so when PR is finite, but P theta is 0. So log 0 is what? It's a very small number, negative, very negative number. That's fine. That means your model will focus so strongly in setting your model probability to be here, but in the two peak regions, it doesn't care so much. So maybe in the end, your output for your model will look like something here. That means you very probably will lose some peak structures. So that's kind of called mode mixing. One is mode mixing, averaging. One is mode mixing. Okay. So from these two aspects, we will say what? We will say that whatever you're using this KR divergence or this KR divergence, you always have kind of drawbacks, very strong drawbacks for your generative model. So how to solve this problem? First, we want to construct some symmetric function, right? Some symmetric distance stuff. And it's really possible. You can construct Jason-Shannon divergence called Jason-Shannon divergence. By combining these two together, so Jason-Shannon divergence between the PR and P model equals to half PR divergence between the P data with PR divergence between the P model with PR plus P model. So this is somehow combining the two measuring way together, right? And this is symmetric now, because once you change the order of the measure, it's the same. You see here, it's a symmetric construction way, right? So let's consider such a problem, such a question, that how to change our training guidance to be such a JS symmetric Jason-Shannon divergence, which combines the advantage from both this KR divergence and this KR divergence. We know that for the variation autoencoder, we know how to evaluate this measuring way for the KR divergence, because the integration for the real data, something you can convert it into the estimation that you make a lot of example from your data distribution function, right? This is possible to do. But here, for evaluating an integration of model, log, including the data distribution, this is very hard. First, we have no such a way to convert this integration to be such an estimation. Not obviously, even though you can't do that, you just sample a lot of the P model. You sample a lot of the data samples using your generative model. You can do this, but we have no way to approach this P data distribution function for a given fantasy samples. This X is a fantasy sample, but this X is sampled from your model here. For a given generated example, using a generative model, you don't know how to estimate the probability that this X will appear under the true data distribution function. This is super hard. Okay, so how to do that? And also, let's try to ask again, what's the motivation to have this term here compared to with term only here? This term will do what? We are trying to avoid this part, right? This part is bad if we only use this KL divergence, right? This part quite often will happen once you are only using this KL divergence. So adding this term, the very first motivation is trying to punish this situation happening. And we say that in this case, that means you are generating some data points are very far away from the data distribution function, or let's say you are generating some fantasy examples that in principle shoot with 0 probability density, right? So in this case, how to punish it using some other way? So what GAN is doing is replacing this KL divergence, this part, using a binary classifier. And this binary classifier will do what? We're trying to classify the data points generated from the model and the data points from the real data pool. Because we say that once you are having this situation, because the probability estimation for these two kinds of distribution function are already very different. So easily you can find some decision boundary to separate these two, right? Once you have the ability to separate these two kind of data examples, you just reject all the examples from this model. So you are kind of push down this part, right? So here, the strategy for GAN is trying to punish this overweighing low density region. Use a binary classifier. That's what GAN will do. So this basically derives us the motivation to introduce such a classification, or in GAN, this is also called adversarial training. And what GAN will do is trying to teach a discriminator. So you will introduce discriminator, discriminator. Discriminator is basically this binary classifier. This discriminator will distinguish between the real, the real and the fake data distribution functions, right? Like some points are from the p theta of x or from the p real of x. The discriminator will learn to classify these two different classes, right? Okay, so let's say a general GAN framework now. As we said, we need to have a discriminator introduced. So discriminator, and this discriminator will try to map any data point x. So suppose our x is with a key dimensionality. It will map this x to a scalar score, because this is what? This is a binary classifier. So you will try to classify. Once x is real, you output a number 1. Once x is fake, so I will use tilde x to represent this is a fake x. You want the discriminator to give you an answer 0. So this is a fake, right? So the purpose is trying to distinguish. And also you have a generator, right? Generator, let's call it a G. The G, we're trying to, again, we also have the latent code exception. Because as we said in last lecture, latent variable models can take advantage of the real data properties. We know that the real data, the real data from the world, from the nature, they actually hold some manifold exception, and also they can take the full advantage of the latent code model. Once you can access into the latent manifold, you can do the linear combination of your data sample easily, right? So this is so good. So here in GAN, we also use this latent code exception. So we start from some latent variable z, or people also call it some noise, some randomness source. Let's suppose this latent code is from a d-dimensional space, and quite often we will just assume a very simple prior distribution function for this latent code. So this generator will map this random noise or this random latent code to be a x. And x, as we said, it's belonging to this key dimensional space. So basically, this generator is a function. So this is defining as x tilde equals g of z, right? And you have some parameters theta being encoded. And if you do this process, example, a lot of z, and you throw this z into your function g, you get a lot of x, you will have a probability distribution function for x as well, right? So let's suppose all the generated x tilde, they are following such a p of g function with the model parameter theta, okay? And as we said, the goal of the generator is trying to let the distribution function from our model. So this is our p theta, our model distribution function. We want this to approach the real data distribution function as much as possible, right? So here, to achieve this point, again, we will try to let the generator to have the ability to fool the discriminator or trying to trick it. You train a generator to let the discriminator thinks your generated x tilde is real. You try to let the discriminator to be fooled by throwing some x tilde there. But meanwhile, you also train your discriminator to have the ability to clearly distinguish the input x is from the real data or from the generated ones. Okay, so let's plot this structure here. As I said, we have some real data distribution function. Suppose it looks like something here. This is the real. Yeah. That's your collection or your observations. Right? You have your real x. Meanwhile, we want to construct a generator. This generator might look like here. I plot it in this way because usually your latent space Z is holding a lower dimensionality compared to the data distribution, to the data dimensionality. So your Z dimensionality is lower than the data dimensionality. This can let your network to be with smaller inputs, right? Okay, so by repeating this generator function a lot of times, you will also get some distribution functions. You call it, for sure, this is fit, right? And you can call it x tilde. And as we said, x tilde equals g of z. This is parameterized use the parameter theta. And then you throw this x into a discriminator. So what discriminator will do is trying to distinguish the input x is real or fake. If it's real, it will trying to output number 1. If it's fake, it will try to output 0, right? But once you have some trained discriminator fixed, you will in the next time you try to train your generator to fool the D. So the generator training guidance will always be trying to let dx tilde equals 1, right? This will give some guidance to your generator training. Okay, so this is the basic idea of GAN. Do you have some questions here? If no, let's continue. As I said, this is the GAN framework, and why this structure can be related to the Jason-Shannon divergence we mentioned here. Let's see the underlying theoretical reason. First, we need to know how this architecture will be trained. What's the training dynamics looks like? And the training dynamics of the GAN is very closely related to the game theory. this training is basically mimicking a zero-sum game. Zero-sum game, you can also call it a mini-max game. Minimum, maximum, you perform the minimum and maximum at the same time. Or you can call this is a two competing player game. And let me see how to introduce this logic here. First, we know that we have the discriminator D. The D is trying to do a binary classification, right? You want to do a classification. For binary classification, what's the loss function? Do you still remember? For binary classification, when we talk about the logistic regression is the most simple binary classifier, right? And there we introduced the proper loss function is what? It's the cross entropy. So the loss function for D would be what? That's expectation if X from the real data, then you're trying to decrease this log D, right? And because this D, this discriminator is designed to be a binary classifier, so the output will usually be set to be within 0 to 1. It's a probability, right? By the way, here I need to emphasize again, this D of X, this is a scalar output. And within this vanilla designing, this output, the D of X, is the probability that the discriminator thinks this input X belonging to the real data pool, right? So D by X is a probability. And once the X is really generated from the real pool, then the discriminator will try to output number 1, 100% sure this is a real. Or if it's generated by the generator, it's a fifth one, then the discriminator will try to output a number 0 that it's 0% sure that this is a real data, right? So the output is interpreted as the probability that the discriminator thinks the input X belonging to the real data pool. Okay, so the loss function for D will be what? The cross entropy will have 2 terms, right? Because this is a binary classifier. You have 2 different inputs. One is this real data, the other is what? So suppose now X is from this P theta. So you will try to reduce log 1 minus D of X. That's the cross entropy, right? Why it's 1 minus D of X? Because the probability that this X is classified into a fixed one is 1 minus D of X. This is a Bernoulli distribution function, right? Because our generator is sourced from the latent space. So you can rewrite the second term. So the first term will be the same. The second term, we do not have the real access into this P theta, but we have the access into what? Into the randomness, the noise, random noise. So we know we perform the generating process from this Z, right? P of Z, some prior distribution function of P of Z. So you can rewrite this expectation function to be expectation under P of Z. And you can also insert this Z here. By the way, you better write this X tilde, X tilde. So X tilde equals what? Equals G of Z, right? You just replace this X tilde to be G of Z. So this can be the loss function for discriminator. Okay, then for G, what's the G will do? What's the generator will do? The generator, the goal is trying to fool, trying to play trick on the discriminator, right? So it will always try to decrease what? Trying to decrease the inverse of this x generated from the model 1 minus d of x, right? So you just take the second term and a negative sign, put an inverse here. It will try to trick the d. Or in other way, we can say that it's trying to z, p of z, log 1 minus d of jz. Trying to let your discriminator to produce you a number 1 for a generated sample g of z here, right? Why we deleted the first term here for the training of the generator? Because here in the first term, there's no generator parameters being involved, right? So that's also fine that if we just write the first term also here, this is basically adding a constant in the training objective for G, right? Because in this term, there's no generator parameters. The generator parameters is involved in this G of Z. Right? So we just repeat it here. You see what? You see the LD and LG fulfill this zero-sum condition, right? That's why this training dynamics are called a zero-sum game. Or in the game theory, people do not quite often use the loss to be the term. They call it the value function or the payoff. The value function, or you can call it the payoff for the two players, for the two competing players. And people are usually just set the loss function for G to be the value function V. So we can call it VDG here. That's just the LG. And what the GAN will do is trying to minimize for the G. You should understand this G to be the model parameter theta of G, and maximize D. Again, you should understand this to be this theta parameters. Minimize and maximize V, D, and G. This D and G, again, you should understand it to be the fit D, fit G. Okay, so let me write it in a clear way for you. We define the loss function for generator, this function, to be the value function. It basically involves the parameters for generator and also for the discriminator, right? You have the D appeared here. You also have the G appeared here. So let's just use this format for the VDG. And what GAN will do is minimizing theta of G, but maximizing theta of D. And this theta of G, theta of D. But later I will, just for simplicity, just write minimize, maximize G, D, V, D, J. And this VDG equals what? Equals x from PR. It's just a rewriting. Okay, sorry. Z from PZ log 1 minus d of g of z. Okay. Okay. Is it clear now? Sorry, I might introduce some symbol around this. So here, for the classification, for the discriminator, the cross entropy should be here. This function. Cross entropy, what's the cross entropy being defined? Cross entropy is what? Is, if I write it here, if it's minus P log Q, right? There is a minus. Sorry for my stupid roundness here. The loss function for discriminator should be minus expectation data log D minus this. So all here should be minus. So LG, again, taking the negative, it would be plus, right? Plus, plus, plus. So the VDJ, the value function should be defined as plus. Okay, now it's right. Sometimes if you're not unsure about the symbol, you should go back to the binary classification part, because we know for binary classification, the cross entropy is clearly defined. Cross entropy is defined to be minus, let me write it here. Cross entropy between two distribution function P and Q is defined to be minus P log Q, right? And here, once we know that P and Q are binary variables, are Bernoulli distribution functions, you can actually write it to be what? P log Q minus Q log 1 minus Q, right? Because we know this 1 minus Q is the probability that the model thinks it's a fake sample, right? Okay. So the loss function for D is here, the loss function for G is here, and the two loss functions must satisfy this zero sum condition. And usually we take the loss function of the G to be called a value function. And what GAN will do is doing this mini-max gain. So minimize G, but maximize D. And this value function is here, is the loss function for generator, it's plus. So if you write it in the integration way, what's it? This is integration over PR of X log d of X dx. And that's the first term. The second term is what? So P of Z log 1 minus dg of Z d of Z. Actually, you should insert some indicator function that here I just for simplicity, I ignored that indicator function, that letting the g of Z to be equals X. Okay, so this is the training dynamics, this mini-max, this zero-sum game. That's the training dynamics that GAN is performing. And again, we are not clear yet why this training dynamics can be connected to the Jensen-Shannon divergence, the JS divergence, right? So let's write it here. If you have questions, you can interrupt me at any time when some derivations are not clear or you found something wrong I wrote, okay? Okay, so let's do this mini-max game now. And we said the final goal is to have some very good or optimized generator. So let's call it G star. So G star would equals what? Minimize fit of G, or we just write it to be G. What's the loss function here for the G star? That should be max D VDG, right? So you should consider this part as a whole to be the loss function in training your very good, the optimized generator. So how to do that? First, we need to train the discriminator to have a loss function for your G, right? So the first step, let's consider, first step, you fix your generator. Do not touch your G, but you will train the discriminator to what? Here the goal is to maximize this value function. And by maximizing this value function, so the first step, let's train a very good classifier to distinguish the real data from the fake data. So we want what? We want D of X equals 1 and D of X tilde equals 0. As we said, the loss function is the cross entropy, right? You are trying to maximize D of, if X is from the real, this, right? This first term is basically trying to achieve D of X equals 1. And the second term is once Z, you're generating something using our generator, this G of Z. Because this G of Z is what? This X tilde, we call it, right? So the second term we'll try to achieve here. And I ask you one question. What's the optimal D here? What's the optimal discriminator would output here? Let's write this value function. This is just maximize V, right? Let's write this value function V here using the integration way. That's PR of X log dx. That's the first term. Then the second term is what? Is P of Z log 1 minus D of G Z dz, right? And under some condition, this integration can be converted to P theta of X or P generator. Let's call it P theta of X. Oh, let's call it PJ, generator of X log 1 minus dx. Under which condition? Once you can have, maybe I just tell you later. Here I cannot write it. So let's assume it's already clear that we can convert this integration over dz to be the integration over the model probability, our generator model probability here. If this is clear, so you can write it in this way, right? Now you can combine, because here the distribution arguments are already the same. So basically you can combine them together. Log d of x plus model generator dx, right? Is this clear? Because you just combine these two integration together because they share the same arguments, x. It's under the same data space, the k-dimensional data space. So we want to maximize this integration value. And maximizing this integration value is equivalent to maximizing this integration function for any given x. This is a much stronger condition, right? So let's solve this maximization problem using some optimization algorithm. It will give us what partial d over vdj equals 0. We try to solve this derivative, right? And we can set the integration function here. We call it, let's call it fd dx. This fd equals what? Let's set, yeah, it equals pr log d plus pg log 1 minus d. So this can be equivalent to setting partial d over partial fd over partial d equals 0 for any given x. And this is easier to be differentiated, right? This just give us what? PR over d minus pj over 1 plus d equals 0, right? From here, if we apply this partial difference equals 0, we get this. And this will give us the d star. That's the optimized discriminator, which satisfy this training dynamics is what? Is PR of x over PR of x plus PJ of x. This is the optimized discriminator. So see, this discriminator is kind of estimating you the probability ratio of the real data distribution and the generate your model distribution function. Because once you train it to be a binary classifier, in the end, the model output, the optimized model output is this ratio, this PR over PR plus PJ, okay? Okay, now let's summarize it here. This D star for fixing generator X, it's the result from this, right? And this equals PR over PR plus PJ. That's the training for the discriminator. Okay, now let's suppose after training, we already get this. So the training is very good. Once you train your discriminator, the discriminator now is having this solution. So what's the cost function for G now? Or what's the loss function for G? So here, the loss function for G, as we said, it should be this, right? The loss function should be this because we write the GAN training dynamics to be here. Arc minimize G for this. This is your objective. So here the loss function for G or the cost function for G is this. You can write it to be D star J, right? Because we assume after some training, the discriminator here is already achieving the optimal solution. So we can replace the D to be the D star. They do not need to write this max D here. So what's this? It's P real data log PR over PR over PJ. That's the log D, right? You just replace the D star into the value function expression plus P model, yeah, 1 minus D. 1 minus D star here equals what? That's PG over PR plus PJ. And the integration argument is the same, right? Here, this formula is just replacing the D to be D star. D star now is PR over PR plus PJ, right? This is 1 minus D. Now, we can easily insert a half here, 1/2. This will not influence the result, right? You insert this 1/2 in both the denominator and numerator. And what's this? If you still remember, we write here for the Jason-Shannon divergence, this P Jason-Shannon divergence is defined to be the KL divergence between PR and this is the mixing, right? PR and P model mixing, half. This is 1/2. Plus the KL divergence between P model and this mixing. So you have this mixing. And once you apply the definition for KL divergence, you will have this log. This log PR over P mixing, this log PJ over P mixing, right? And it will equals to what? It equals to KL divergence between PR plus PJ plus KL divergence PJ over PR plus PJ, and also have this constant term outside. That's what? That's -2 log 2, because log 1/2 equals minus log 2, right? So these two terms together is the JS, the Jason-Shannon divergence between real data distribution and the model distribution function plus a constant term. So you say, now we connected the GAN training guidance is related to the Jason-Shannon divergence. And this Jason-Shannon divergence is a better metric compared to only the KL divergence, because here this is symmetric. And also you have both aspects, both the sensitive aspects compared to the KL divergence here. Like if you only use this one, you have the mode averaging problem, the mode mixing problems. You will have some very blurry results. If you only have this KL divergence, you very probably will miss some peak structure. They are not so good. Only combining them together, that's giving you the Jason-Shannon divergence. And here it is. Here we have it now for the GAN training. Okay, so this slide is just to show you that using this kind of mini-max or zero-sum game for the GAN training, we are actually using the Jason-Shannon divergence to be the loss function of the generator. If we put it into concrete, that's training the GAN, but training the generator. So we fix the discriminator, train the generator. As I said, the training guidance is minimize this. Right? And this is equivalent to minimize with D star G. And the purpose is for sure to get a better version of the generator. Better version means it can fool the discriminator, to let the discriminator thinks the G of Z is a real data, right? And we also derived that this V D star G is just what? It's just the Jason-Shannon divergence. But let's rewrite it again here. This is trying to minimize the model distribution function over this plus P of z log 1 minus dgz, right? This first term, because there's no theta g being involved, so it will not influence this the mini generator part. So in reality, what you will write in the code is just here. Minimize z pz log right? So you try to minimize this stuff. So you are pushing d of gz, the fixed data input, to be 1. So you are pushing the discriminator to give you the answer to be 1, to be a real, right? And in reality, in practice, I mean, you will find if you really use this to be the loss function for training the generator, your loss can be kind of stopped. That means you have no very effective gradient feedback there. Why? So let's say this case, you need to calculate the gradient. And for calculating the gradient, for sure, you will have this term being involved, right? This log 1 minus d g of z. Yeah. Yeah, right. This equals what? This equals 1 minus d of g of z minus, this minus comes from this minus, right? So in the gradient for training generator, you will have this term being multiplied always, right? Once you are using this to be your loss function. For any parameters inside your generator, the gradient will have this term being multiplied, right? And let's look at this function, this 1 minus 1 over 1 minus d, how it looks like. If we plot it, this is dj of z, and this is 0. This function actually looks like here, This is number 1. It looks like something here. And we know that when we train the generator, we are assuming the discriminator are kind of well trained. So the d are approaching the d star. D star means d star means what? Means for real data, you can output 1, and for a fixed data, it will give you something close to 0. That means the discriminator can, very well classify the real X and the generated input, right? That's what D star can output you. So at least in the beginning of your training for generator, you are located somewhere here. And this region is quite flat and it's kind of 0. That means in the beginning of your training for your generator, you have no feedback for your training. You have no gradient information because this is giving you 0. So in reality, people always change this to be something here. We put a minus, yeah. P of z log d of g of z. It's equivalent to each other, these two. Why? This is trying to let your discriminator to output d of gz equals 1 as well, right? The same as a binary classification, but you're taking this model distribution function to be the real distribution function. So these two are equivalent, but here it's much better compared to this case because partial d log d minus Yeah, because here there's a minus. This equals 1 minus 1 over d. It looks something like here. So this is minus 1 over d, but this is minus 1 over 1 minus d. And we say once we are using this loss function for training the generator, even though in the beginning d of x tilde or d of g of z equals 0, it's something here. It's very big value. So that you will help your training algorithm to punish this case. It will provide you a very big gradient flow to let the algorithm to train it smoothly, right? Compared to this case. In this case, it's 0. You have no feedback. But in this case, you have a very big value for loss function. That means the training will punish it. It will know which direction to reduce it, right? And also the optimum value is here. So when d of g of z equals 1, d of g of z equals 1. This is the optimal value for training generator, because the generator will try to fool the discriminator, right? So we see, even though for this two case, both the optimal value is number 1, yeah, this part or this part, but quite often in the beginning, we know that the d of x tilde is quite close to 0. So you better to use this way to construct your loss function. So in reality, people use this function to be the loss for generator. Okay, now is it clear for you now? This is the second step for training the generator, and we already have the first step for training the discriminator. Once you train a discriminator quite well, maybe a discriminator is quite close to this D star, the optimal solution. And the optimal solution will give you something here, right? The x equals 1 and the x tilde equals 0. And then when you train the generator, you better use something here to avoid such a situation. Now let's summarize a little bit. So first, the whole idea in this minimax game, the key point is what? The key point is to introduce a discriminator. The discriminator can somehow provide feedback to update the generator, right? Along this delta theta of g, or let's see, along gradient d star g, right? So you need to have such a, you need to have such a discriminator to provide some gradient direction for training generator. That's the whole idea or the key point. Now let's assume that D and G are all trained very well. As we said, the loss function for G is actually the Jason-Shannon divergence between PR, P model minus 2 log 2 a constant. And this will achieve the minimum point if and only if Pj equals PR. Right? That's why we can use this to be the loss function for training GAN, and our goal in the end also achieved that we are approaching the data distribution using our model Pj. And let's assume the Pj is already PR. So when Pj is already PR, what's the loss function here for generator? In this case, we also assumed D star is achieved. So D star equals PR over PR plus Pj. So now, because the generator is also very well trained, so Pj equals PR. So this equals what? This equals 1/2, right? 1/2 means the binary classification is just very confusing always. That's because your generator is actually a super good generator. It can generate you some samples. It's not distinguishable to the real data. So you cannot call it fake anymore. It's the same as the real. So in this case, the discriminator will for sure can only generate you some confusing answers. And in this case, LG equals what? Equals minus 2 log 2. So this is the optimal value for the generate loss function. Okay, so this somehow tells us the optimal solution for this GAN training will give us our desired result because we desire this, right? We desire PG equals PR. And in this case, D star equals 1/2. And some people will explain it using this plot. So maybe in some talks, you will say people use this plot. This is the loss surface for both G and D. It might looks like such a little bit complicated surface, yeah. And usually your first step is trying to maximize this value function. Try to find a very good binary classifier. So you maximize, this is some function looks like this, right? You try to find which value can maximize the model parameters for the value function. So you will find some solutions here. This is your D star. And the next step, you were trying to minimize G, VG, D star. So it will look something here. Oh, sorry, maybe the first step is here. This is the first step. First step is here. You find the point here, yeah. And the second step is here. So you try to minimize it, maybe it's located somewhere here. So just imagine you have such very complicated loss surface for both the D and the G. And usually in your first step, you do a maximization to find what's the best discriminator. So you find somewhere here, this is your D star. And you have a lot of D star once you change your G, right? So then you tune your G to find this minimization problem's solution. It will do the minimization in this direction. So finally, you have this. Okay. So what's the pseudocode you can write once you want to write it into the algorithm? The pseudocode, you can write it here. Suppose you want to train it for some number of training steps, for some epochs, or you can call it. For each training epoch, you sample some real data. Let's say you sample n training samples, training data from the training set, right? X1, X2 until Xn. And you also sample some random noise from P of Z m times. And you throw this sampled random noise Z into a generator, you calculate, so you compute the X tilde using a generator. Then you want to update the discriminator. So you compute the discriminator results on X and X tilde. But to calculate the loss function, you need some label. But here, the advantage is you know how to label it very easily, right? You just label all the X to be with the class identity 1 and all the X tilde to be with class identity 0. So you can calculate the binary cross entropy, right? That's your cost, or cost for your discriminator. It's just 1 over n summation log d of x plus log 1 minus d of x, right? This is actually x tilde. Once you have the evaluation for the cost function, you do the fix d, train d, or update d. That's just fit d equals fit d plus some learning rate times this cost function, cost of d. So now you trained your discriminator. In the next step, you train your generator, but you fix the discriminator. And as we said, the goal of training the generator is trying to fool the discriminator. So you label purposely the x tilde to be with class identity 1. And as we said, to avoid the zero gradient information in the beginning of the training, you change your cost of generator to be what? To be just this log d x tilde, right? We're not using this log 1 minus d, but using this log d directly. So we perform the training, but first you fix the d, update the generator. So theta g equals to theta g minus learning rate times this cost of j, right? Here this maximizing, here this is minimizing, right? As you repeat this 1 and 2, repeat 1, 2 alternatively. In the end, you will have both a good generator and a good discriminator. That's it. That's your algorithm constructing way. Now let's look at some code examples for you. I just very briefly show you the idea in the code. So, yeah. Yeah, here. So we are again using TensorFlow and with Keras to be the model construction way. And here the data we're using is a very funny data set collected by Google that this website, they let many public people to draw some sketch randomly given the class identity. And they will specify some class identity like bicycle or castle or flashlight or something very popular in reality life, and let you to imagine and draw a sketch for that. So we focus here only on the bicycle. That's what people plot for the bicycle, a lot of such sketch, right? So that's our training data. So we will train a generative adversarial network to learn how to draw some picture looks like here, and also share the same distribution function that we want. So this is the data set here. This is loading the data set. And now let's construct the discriminator and the generator. Here we specify some architecture parameters. That's our hyperparameters, including the learning rate and the convolutional layers parameters like the number of filters and the filter size, such stuff. So this part is our discriminator. So what the discriminator do is trying to do a binary classification for you, right? So the input is this image, and the image size is 28 by 28 grayscale pixel matrix, right? That's our input, and we use convolutional neural network for constructing the discriminator. Output, because we are doing a binary classification, so quite often you will use a sigmoid in the last layer to convert the model output to be a probability. So that's our discriminator, yeah. And for the generator, it will start from some random noise. and this is, we call it the Z dimensionality. And here, the Z dimensionality is 100. So it's a 100 dimensional random noise distribution function. And here we will use a Gaussian distribution function to be our latent price base. Okay, so that's the generator input. And the generator is also using convolutional neural network, but for sure it will start from a dense layer to invert the noise, the prior noise, to be something longer, right? Bigger dimensionality, and then you can reshape it into a picture-like stuff. So that's why you see there's a reshape here. And after this, you can trying to increase the picture size to be, in the end, it's 28 by 28. To do this, you can use upsampling 2D, or in last lecture, we said that in the VAE, you can also use the convolutional 2D transpose. This is kind of a way to inverse the convolutional operation, and you can also control the output size for you. So just be careful about the dimensionality matching to be sure that in the end, the output size is 28 by 28 by 1. And here, this is giving a one structure for this. So that's the generator. Okay, now, as we said, we need to do the training separately for D and J, right? For discriminator, this is quite obvious because your input is just whatever X or X tilde, the real or fake. So you can compile the discriminator directly, and the loss function is binary cross entropy, right? This is quite obvious. But for the generator part, because we say that there is D involved in the loss function for G, right? So you are actually minimizing log of D of G of Z, right? You have the D being involved. So you need to combine these two models together to construct the model for training generator. So let's do that. First, we need to change the trainable properties for discriminator to be false, because when we want to train the generator, you need to fix the discriminator, right? So this is to fix the discriminator for you. It will let all the parameters inside the discriminator network being fixed. And then you start from some random noise, that's your input, and you throw this input noise into the generator, you get the generator model input, and then you throw this this is what? This is G of Z, right? G of Z. This is your X tilde. You throw this X tilde into the D discriminator. That's your model output. So this 3 line is combining your training model for G, right? Input is the Z, random noise Z. Output is D of G of Z. Then you can do the compilation. And again, the loss function is binary cross entropy. Okay. After that, we can set up some function for training the GAN. So this is separately done for training discriminator and training generator. For training discriminator, we need to do the label manually. Yeah, so we do the label for real. Real target is 1, right? We label all the real data samples to be with class identity 1. And for all the fake sample, the one generated from generator to be with label 0, right? This is to do the label we wrote in the slide. Now you train it. So you throw the real image, yeah? So this 2 line is example some batch of training examples from your training dataset. And you calculate the loss function, right? The loss is discriminate.train on batch. You throw the input, the X in, the output should be this label, real target. And you do this on the fake images. You just change the input to be the fake image and the label to be the fake target. And in the end, the total loss is half of it, because you suppose there are half data samples are from the real, half data samples are from the generator, right? You are not doing imbalanced stuff. We are doing balanced training here. That's the training for discriminator. Then the training for generator is easier. We just want the generator to fool the discriminator. So you purposely label all the generated examples to be with label ones. So you take this to be the output here, yeah, to be a training output, calculate the loss and accuracy. And then you throw these two functions into a training organization. Here it's just trying to organize the mini batch sampling and the noise extractions. Noise is generated by this NumPy random normal. And that's telling us we are using Gaussian distribution function to be our prior latent space here. That's the Z, right? That's how you sample Z from. Okay, so once you perform it, you can generate something here, right? It looks like the bicycle, just for the wheels, it's all kind of all four wheels. But inside the training data set, we actually have different kinds of bicycles. Like you have many bicycles with the wheels is a blank circle, right? This is a general problem for the vanilla GAN. That's the mode collapsing. So the GAN will quite often only pick up some very easy solution, like it pick up this kind of solutions, because for this kind of solutions, the discriminator will be confused. It will always give you a very good classification result. Then the generator are not really capturing the whole mode. And to solve this mode collapsing problem, people actually proposed some different metric. It's the Wasserstein GAN, or the gradient penalty Wasserstein GAN. It's replacing the metric from Jensen-Shannon divergence to be the Wasserstein distance. But currently we have no time. But I hope that now you have the ability to understand the mechanism for training GAN, and you also have the ability to read much more fashion works using GAN, like even for this WGAN or WGAN GP papers, you can understand it by yourself now because you know already the very basic ideas. In this WGAN or Wasserstein GAN is just to replace the training objective from Jensen-Shannon divergence to be the Wasserstein distance. It's also called Earth mover distance. There are no other new stuff. Okay, so I think we can stop here. Yeah. Do you have questions in this very fancy training dynamics, this GAN?